Among premium wines, about 25% of faults identified are classified as reduced, that is, characterized by hydrogen sulfide and related sulfur-like off aromas. In such wines, hydrogen sulfide, which has the distinct smell of rotten eggs, is typically present at suprathreshold concentrations. While hydrogen sulfide is highly volatile, in combination with components of the wine matrix, it can lead to the formation of malodorous volatile sulfur compounds. Winemakers have several options for remediating excess hydrogen sulfide before bottling, namely copper fining. To illustrate the chemical implications of copper fining, let's consider a wine that has developed excess hydrogen sulfide. We can add copper sulfate to bind hydrogen sulfide and form Copper-Sulfhydryl complexes. But whereas these complexes were previously thought to form a precipitate that could be removed, recent work by Clark has shown that instead, the complexes form nanoclusters that remain dispersed in the wine. And that means they can serve later as precursors to hydrogen sulfide. In fact, at least 79% of the copper added during fining was found to remain in the wine after racking and filtration. Having been treated, the wine goes into bottle smelling fine. But after storage, hydrogen sulfide can reappear. Since Copper-Sulfhydryl complexes in the wine can serve as precursors to hydrogen sulfide, we are interested in quantifying them. While they are challenging to measure directly in wine, previous work has demonstrated that these complexes can be disrupted by diluting wine in a concentrated sodium chloride brine solution. Once hydrogen sulfide is released, the complexes can be indirectly quantified by measuring the released hydrogen sulfide instead. This brings me to the objective of my work, which is to answer the following questions. 1. How can we more readily measure brine-releasable hydrogen sulfide? 2. How does brine dilution work, and is it measuring all the hydrogen sulfide bound up in Copper-Sulfhydryl complexes? And 3. How does wine composition affect the stability of these complexes? The brine dilution assay I've adapted uses common winery lab glassware and inexpensive consumables. Starting with a wine sample that has Copper-Sulfhydryl complexes, the sample is diluted tenfold with sodium chloride brine. With hydrogen sulfide released from complexes, the sample is then sparged with nitrogen. Hydrogen sulfide is quantified on a gas detection tube where a colorimetric change is recorded and converted to a concentration. The analysis takes less than 15 minutes per sample. So, it would be useful to know if there's any way we can test if a wine will develop sulfur-like off aromas before it leaves the winery. Let's say we have a copper-fined wine and we want to know if those Copper-Sulfhydryl complexes are stable. We could put the wine through normal storage and see if hydrogen sulfide develops, but that's not practical or predictive. We've discussed that brine dilution can be used to disrupt these complexes, and high-temperature accelerated aging conditions are also capable of releasing hydrogen sulfide. However, both these methods have been shown to overestimate the amount of hydrogen sulfide that would develop in normal storage. And this comparison suggests that a wine can have hydrogen sulfide precursors of different stability. I investigated that stability further by producing Copper-Sulfhydryl complexes under wine-like conditions by adding hydrogen sulfide and copper sulfate to different solutions. What I did was vary the amount of time between adding the complex-forming reagents and diluting with brine. The amount of hydrogen sulfide released from brine dilution is shown here in green for a real wine and blue for a model wine. When brine dilution is done immediately after the reagents are combined, there's no difference between the real and the model wine. However, after just 20 minutes of pre-dilution incubation, model wine releases significantly less hydrogen sulfide, while real wine is unchanged. So what's the important difference? Real wine actually contains lots of sulfhydryls besides just hydrogen sulfide, mainly glutathione. In fact, when I did the same experiment using a model wine with an addition of glutathione, what we see is a stability profile that closely resembles that of real wine. To illustrate what this means in terms of complex formation, take hydrogen sulfide and glutathione in this representation. In wine, they're not present at 1-to-1 ratio, but more like 1 to 100. And when copper is added, some might complex with hydrogen sulfide, but it seems more likely that glutathione will actually get in the way. And in fact, organic sulfhydryls like glutathione are known to terminate polymerization and condensation of copper sulfide complexes. We found evidence of this in model wine, so we next applied it to different real wines. What we saw across different wine styles was that after 20 minutes pre-dilution incubation time, when glutathione was added to the complexes, more hydrogen sulfide was released by brine dilution. That is, for every wine, more of the unstable complexes are formed with glutathione, shown by the taller red bars, than without glutathione, shown by the shorter blue bars. What this means for winemaking decisions is that brine dilution has the potential to test if a wine has formed stable complexes after copper fining. If we take a finished and fined wine, do a brine dilution, and no hydrogen sulfide is produced, there is a good chance that this wine has stable copper-sulfhydryl complexes. On the other hand, if brine dilution does release hydrogen sulfide, we have identified the potential for hydrogen sulfide to appear during storage. Our results indicate that copper-fined wines that are higher in glutathione are more likely to form unstable copper-sulfhydryl complexes capable of releasing hydrogen sulfide when compared to low glutathione wines. As we finalize data on the native glutathione and copper in our samples, we will continue to refine our understanding of the factors influencing the stability of copper fining treatments, and thus the potential for this approach as a predictive tool.